Hey, hello, my name is Jan and welcome to this tutorial. Today I'm going to show you how I made the VJ loop I posted on Christmas, and it will be heavily focused on Tyflow and Krakatoa. So the first segment will concentrate on Tyflow and the second segment will concentrate on Krakatoa and Magmaflow. Okay, first things first. We will go to the Customize tab and go to the Unit Setup, and you will see I picked meters as the display unit scale. 1 meter per unit. Alright. And in the time configurations I chose PAL, or 25 frames per second, and I picked an animation range of 1000 frames. Okay. But let's begin. So for this animation you don't need so many objects. Actually you need a light, a camera and a tube, and that's it. So let's go into Tyflow. Okay, I'm going to create the Tyflow object and I press Alt W to enlarge the perspective view. Okay. Now let's set up the Tyflow simulation. First you will see I'm not doing very much, but to create 10 particles in the range from frame 0 to frame 300. And of course I take the position object operator and pick our tube. By the way, the tube has these measurements: rotation to -90 degrees on the y-axis and these coordinates. The location of the particles will be in the volume, so I pick volume in here, and that's it for this operator. I guess the best thing for the entire rest of the tutorial will be if I make the tube invisible. Okay, you see these little dots? These are the particles we emit. Go back to the Tyflow. So now the particles need a specific movement. So let's jump right into the C# scripting. We don't need to pick anything, any script accessible objects or texture maps. We only get into the script. Delete the comment brackets. And delete everything in the for loop except this, the declaration of the particle index. I have in mind that the particles should move along the x-axis and go in spirals around it. So how can we do that in scripting? Let's get back and we will create a new 0.3 object and we will call it x-axis, which is simply the x-axis itself. And then we need our position of each particle at each frame in regards to the x-axis, and we will create a new 0.3 object for this and call it yz position or just yz pos. And this will always have a 0 as the x component and the original y and z components of its position. Point y to separate the y component, and then of course the same thing, but point z for the z component. Okay, what can we do with these two vectors? We can create a vector cross, and right now this would be spirals around the x-axis from their position. Cross yz pos normalized, because the length of the vector will be irrelevant for us. Only the relationship of both vectors counts. Okay, let's have a little preview. So setting up the velocity for the index or sings by taking up the value of spiral. Yeah, everything's fine, and let's have a look. Maybe it's better to make the display of the particles in large dots mode. Okay, if I press T for top, you will see the particles will only move in circles around the x-axis. There's no movement into the x dimension. But for creating spirals, we should change that. Press P for perspective mode again. Go back into Tyflow, into your script, and add the x-axis itself. And maybe multiply it with 0.5. Okay, perfect. You see a constant movement into the x direction. If you press L for the left view, you see they are still moving in circles. Okay, as I think this would be a little bit boring in its movement, I'm going to add some turbulence in it. And this is also represented with a function in Tyflow. And for that we will also create a new object or a new vector, and we will call it turbulence. And the function is called getTurbulence. First argument will be the time. Second argument is the current position in the force field, if you want to call it like that. The third argument will be our frequency. I would say we will take a very low value because I don't want the force field to wave too much or to be too significant. So 0.05 f, of course, because it's a floating value, will be good enough for us. And the fourth and last argument of this function is our scale. And this will also be a very low value to make the impact of the turbulence very slightly. Okay, and then we will add the turbulence to our velocity. Let's take a look. From top, I'm going to put in a spawn operator with the option of travel by distance. I would say the step size is 0.1 meter. No inherited properties. And of course make them visible. Select the display operator, press Shift, drag it into empty space, maybe set another color, and connect it to the outlet of the spawn operator. And then let's see. Alright. That's cool. But I would like some more variation. And I will do this again in the script operator and multiply the spiral value with a very tiny range of random values like 0.9 and 1.2. And also the turbulence will get multiplied by a random value. The maximum value will be a little bit higher, like 1.6. One more bracket closed for this function itself, or its arguments. Okay, everything's fine by now. Okay, let's take a look again. Here you see these dots. They are much slower than the other ones. And now to our next script. And this will regard the texture coordinates and also the deleting times or the lifespans. Take a new script operator. And once again, no texture or object will be necessary for that. But this time we won't delete so much of this, because there are a few things to set up at the particle buff. And for that we will use custom floats, just to have the values accessible in other if clauses or in the else case. Let's create our first custom float with a channel number 0, and the entry will be a random float for later. And the range will be a bit higher, between 1.5 and 2.5 5. Also, we need at the birth of the particle another custom float with the channel number of 1 and the initial value of 0. But this will change later over the lifetime. Okay, last but not least, we initialize at the particle birth the third custom float channel, also with a random float, but this time with very large values. I would say between 333 and 444. So now I'm going to set up the case when the particle is already born, and that's the case when the event age is not 0, and then the values of our custom float channels will change. So our channel with the channel number of 1, which was initialized the value of 0, will collect the traveled distance of each particle. And how do we do that? Pretty easy. We will add to the current value of this channel the magnitude of our current velocity divided by the step size. In this case, I will divide it by 8 because I will set up the Tyflow time step value to 1/8 of a frame. Almost forgot to mention. And then we will create another custom float. This custom float's entity will be the value of the traveled distance divided by the random float, which was set up at the birth of the particle, which will determine the end of the path of each particle. So everything left we need to do will be to check if this result will erase over the value of 1, and if this is the case, the particle gets deleted because it's the end of the path. So we will check our custom float channel number 3 and compare it if it's greater or equal to 1. And then we will call the action, and the action will be delete the particle. And at the end, just like I did at the original VJ loop, I'm going to change the velocity once again by getting the velocity and multiply it with the custom float we set up at the birth of the particle. But you don't need this. You can also leave this line out. But what you definitely need for Krakatoa later is setting up the texture coordinates by picking the function set UVW, because that's the default texture coordinates channel, and putting in a vector with the x coordinate of the current spot of the particle, and the y component will be simply a 1 because we don't really need that, and the z component will be simply a 0. I forgot. And let's check with the display data operator our mapping. Okay, perfect. And the particles will disappear when their x component goes close to the value of 1. And that's the case. Alright. Now the cool thing is that these values of our texture coordinates will be inherited by the spawn operator. Let me show you. Maybe it will be helpful to show it with a vertex color operator. I only use this for demonstration, so don't worry. Alright, there you have it. The entire gradient walks along the spline at each individual spline because they all have different lengths. But this was just for illustration. That's not what I want. But I will leave the spawn operator here. So I want spawn particles to move a little bit before they slow down. So I need to save the position of them on the entry of the event. And I'm going to reach this by taking the position and saving it to the custom vector channel of 0, I would say. Okay, and then I will adjust some turbulence, something about the strength of 0.3, and a low frequency like 0.1, and a scale of about 0.4. And in the turbulence mode, of course. And that's it. Yeah, and that's that's okay. Go back to the force operator and set a keyframe with the strength to 0. And the automatically created keyframe at frame 0 with the original value of 0.3 right here will be moved to frame 50. So the decrease of turbulence strength will happen between frame 50 to 200 within 150 frames. Okay, that's not better because we actually need, for getting back to our initial position of their creation, a find target operator. Some of you will remember from another tutorial of mine. Choose the mode controlled by velocity. Test is true if the value is beyond 0.001, so the force will always be applied. Acceleration a bit higher to 6, and the target location will be our custom vector of 0, which we set up here at the beginning. I forgot to synchronize the keyframes on the event age. Okay, you see, the whole animation of the force strength is visible here at the particles which were already older than 200 frames, and the decrease will begin somewhere here, I guess, after 50 frames, like in our keyframes setup. Okay, but they are a little bit too wild, so I'm going to set up a particle bind operator. Put it down here. Stiffness will become 0. Okay, go down below, check all the other values. Yeah, and everything else is fine. Next, I'm going to check their age, their event age. And if the event age is greater or equal to 30, they switch over to another event where the find target operator will also be enabled, and also the force operator, but the strength will be higher. It will be 1.5 because the force of the find target operator is higher than before. It will have a velocity strength of 20 meters and an acceleration of 20%, but everything else will remain the same. Yeah, and let's take a look again, but with another color, like blue. Okay, let's take a look again. Okay, that's cool. And so I'm okay if they will die in here after about 270 frames, but with a variation of 30 frames. Let's take a look. Okay, you see, they will get deleted, but not so clearly, so sharpen, but with a little bit variation. Okay, last thing for here. I'm going to choose a little variation on the property test, because the cool thing about particle bind physics is that if they switch over to another event, but not so clearly particle per particle, then for a short moment they will flatter a little bit. And yeah, that's the case in here, you see? And later in Krakatoa, this will look a little bit cool, this will look a little bit shiny if we use the magnitude of the velocity in this particular spot. Yeah, this will be cool. Alright, that's it for the splines themselves. Okay, next will be the emitted particles from the splines. This will also work with the spawn operator, which we will place in here. Route them to another event, like here. Choose white, just to distinguish, and also per travel distance. And right now I would say I will decrease, just for computing time, I will decrease the step size in here and also here. At the end, the step size should be the same value of both spawn operators. Okay, and this time I'm not going to change anything about the inherited properties. Let's take a look first. That's already cool, but to have a little bit better look at everything that happens, I'm going to slow them down a little bit with a slow operator, and the slow strength will be very decent, about 2%. Okay, at some point they will stuck. That's good, but of course they also will need a little force field. This will be a turbulence without any keyframes, but with a very tiny strength of 0.05, also frequency of 0.1, and also a scale of 0.04 turbulence mode. Okay, they will be deleted 90 frames after their creation, this time without variation. And that's okay. Alright, that's good. Okay, now before I export, let me explain something. I don't want the tips of the splines, so I'm going to group them with the operator particle groups and put them into particle group B. All the other particles, like the splines themselves, will be in particle group number A. And also for Krakatoa later, as you also might remember from other tutorials of mine, I'm going to give them material IDs for the material ID channel, and they will be in material ID number 1 if they are not the smoke particles or the emitted particles from the splines. Otherwise they will have the value of 2. Final step, increase the step sizes of both spawn by travel operators to the same value. I chose the value of 0.04. And then let's go to the export options in the export particles operator. Choose PRT for Krakatoa, of course. Export the frame range from 0 to 900, that's good enough for us. Under general settings, choose the export group A. No change at the simulation groups, I almost forgot. Yeah, go to PRT settings. We want the ID, the age, go to cache. We would get asked for this otherwise later, because Tyflow doesn't calculate the age in its cache automatically. Position, velocity, mat ID, and our texture coordinate. Yeah, that's it. And I would recommend you to export a partition range of 1 to 3 for the loop itself. Because all the seeds in the script operators and in the spawn operators and so on, they will have a little variation in each partition, and this will result in the loop to have a much longer duration. But you will see later. Pick your output path and then let's start generating your PRT file sequences. Like I said, from frame 0 to 900 with 3 partitions. Okay, now that the export is over, it's time to put Tyflow in here. and disable it and make it invisible. Yeah, just to have a better view. Okay, but now actually it's time to create the PRT loader. Press Shift. Alright, and then choose your partitions. Press Yes to load all your partitions. Okay. Disable it in render and in the viewport. That's okay, because first partition is enough for us by now. But let me do some other settings here. Viewport mode, load every nth particle.
This is for you.
And also press range to limit it to the custom range, and choose blank and also blank for showing nothing before and after the first frame, after the whole sequence is ran through. But we will come to that later when it goes to making the loop. Now it's time to go into Magmaflow. So here in Magmaflow, press S for system, O for output, and then choose the viewport color. That's good, because now as output we will manipulate the emission, and Krakatoa wouldn't show us the results of the emission channel, because by default Krakatoa shows the results of the color channel. Alright, press I for input channel and then choose texture coordinates, and then press I for input texture map. Enable texture coordinates. Drag the wire into here, and then it's time to pick a gradient. How about this one that I showed before? Okay, to make it easier, system, elbow, connect the elbow into the channel PRT viewport color and into emission. Update, and let's have a look at the sequence, which is right here. You know what? Maybe it's a little bit irritating with the y-axis or a y component of our texture coordinates, but no problem, we can solve this in Krakatoa once again. It's nothing too late. Select the wire from texture coordinates to your texture map, press C for convert, choose breakout or press B. Once again, select this wire, press C, and press V or choose to vector. So now we only have the values from our X component and nothing else, because there will be 0 and 0 on Y and Z components. Let's update. Yeah, it looks pretty cool. It's cool that we have this texture coordinate along each spline, and that we let this correspond with the gradient we made. Let's have a look at it in Krakatoa. Switch to Krakatoa as a render engine. As always, I make the output size with a 9920 to 820 pixels. Okay, at the loops I made it 4K, so twice as much in each dimension, but that's not so important right now. Just take a first look. Okay, it doesn't look so cool, but that's first because we didn't enable the emission channel. Yeah, that's because our density settings are not correct. And we also didn't enable absorption, which we'll need later. But first of all, I will change the color of our particles of the PRT loader. But I won't do this in Magmaflow. I'm going to choose only one generic color, which will never change. And that will be pretty dark and greenish. That's too much saturated. Okay. Alright. So the color is finished. And now we will change the light density settings to 1.5 to the power of -2. Enable absorption and then take a look again. Looks better, but it's still too thin. I'm going to decrease the emission strength in here. So it's only slightly a little bit, yeah, looks much better. Override the background color like this. 007 like James Bond. Take a look from a little bit closer, because only in the dark spots where the light is already absorbed from particles from the outside, you can see the emission itself. But the cool thing of Krakatoa will always be how you can manipulate the colors with Magmaflow. For example, by using the magnitude of its velocity. And that's what we will do right now. Press I, input channel, velocity. With velocity selected, press V for all the vector options and then choose magnitude, or press M on your keyboard. Press the slash for dividing, or otherwise A, and then choose divide from the dropout menu. I guess we will divide it a little bit by 3 because the magnitude will be pretty high. Multiply this here, press A and then press U on your keyboard, or select multiply here, drag it in, take a preview look in the viewport. Okay, could be cooler, could be too bright, but I already changed the emission strength multiplier, the final multiplier. Yeah, because I already tested and these are the final settings of the VJ loop. Okay, let's take a look again, make a render. Okay, looks a little bit different, but there's still some things to change. How about if we will multiply the result of the divided magnitude of the velocity by the power of 2. Take a look. Okay, that's cool by now. But it will change by its lifetime. Press I, input channel, of course. H. As we already know, these particles will automatically die after 90 frames. So with a frame rate of 25, the dying age, which will be measured in seconds, will be around 3.5. So I'm going to divide it by 3 to have the last half second of its lifetime completely without any emission. Press minus and subtract this from 1, and then press F for functions and choose clamp to let these values stop at the minimum, and this will be 0. Press A, because we also want to multiply it by the power of 0.5. So the decrease of the value or the multiplier won't be so quick, because it's a floating exponent lower than 1. And last but not least, press A, choose add or D on your keyboard, and add this to it. Let's see how much this is changing right now. We will get a better look at this if we just render it. Okay, it's still a little bit bright, but I'm still going to add a certain value, a value of 0.5, to always have a positive value with which the color gradient will be multiplied, and then we will use the result of the multiplier, scale it down by multiplying it with 0.4. Oh, I made a mistake. Shouldn't be add, but it should be multiplied. Okay, now it's much more what I was thinking of. Okay, but let's go on to the flickering particles. Choose the ID channel. and then create a model of 300. Go back to the ID channel again. Go to functions and uniform random. Make it generate values between 0 and also 300, like in the model. Press C, an integer, and now we can choose our logic operator. Press L, choose equal, or press E, drag a wire into empty space, choose logic, and then choose switch. So now we have our cases. If it matches, the if true input goes through that operator, and if not, the if false case happens. And the if false case is this, because if they are matching, we will let through a white color. Press I for input vector. A vector is also a color. And then produce a very bright yellow. Alright. And this will also be multiplied with a random value. So go again to input ID, choose function, uniform random. Yeah, and I would say it should give us values between 0 and 25, and then multiply our color with this random value. Okay, but before we end, I'm going to include a periodical flickering behavior, and this could be done by using cosinus waves. And how do we do that? First, I'm going to input a script to catch up our current frame, and the code is current time dot frame divided by frame rate, and I will multiply it with pi divided by 2, brackets closed. Okay, that's the entire script. Drag a wire into empty space, choose trigonometry, choose cosinus, then we have cosinus. For example, at frame 100, this number or the result of this would be 4 for each particle, because it orientates on the value of the current frame. That's a global value, and 4 times half pi or 2 times pi represent an entire cycle of the cosinus wave. So 100 frames equals the entire cosinus wave. But I'm going to change that by once again, and for the last time, I'm going to add another uniform random. And this time I will generate values between 0.5 and 2. So the whole cycles of these cosinus waves, which we will see as periodical flickering, will be different. So before I go into the cosinus, I'm going to press A, because I want to multiply it with the random value. Go into cosinus, then we have the cosinus wave. I guess you all know how the cosinus wave looks like. Begins at 1, goes down to 0, goes down to -1, goes back to 0, and then it goes back to 1 again. But we only want positive values. So I'm going to add to the result of all this a value of 1. So now the whole range goes from values of 2 to 0. So I'm going to divide it or scale it down and divide it by 2. So I still have the range of values between 1 and 0 or 0 and 1. And now it's time to multiply it with our cosinus wave. And then we finally have our if true case, when the model matches and we get a flickering particle instead of a colored particle by the gradient. Let's take a look at our result. I made a mistake. I chose the plus button on my keyboard, which will create the equal operator, but that's wrong. I wanted to put the add operator. Okay, now it's all correct. Update. Everything is fine. Everything is evaluated, so let's render again. Okay, not so much to see of the flickering particles, but don't worry, as this Magmaflow only controls the particles of the splines at the end. So I guess it would be best to multiply the result of our switch with the cosinus wave. Okay, let's take a look. Okay, now you recognize that the particles are flickering and that the modulo and uniform random has picked only a few of those, but don't worry though, because like I said, we are going to apply this on the splines only later. I'm going to multiply it with the h, with the first eighth of a second. Apply the function of clamp to not let it overthrow the values, which will go over 1 after 1/8 of a second, and then use the blend function. Okay, this will be our blend amount, so we will blend over the beginning of the particle's lifetime from value 0, which will be the bright white, maybe a bit brighter. A multiply by 2, go over here and take this as our output. Let's take a look again. Okay, that's completely fine. Okay, last thing would be if we let the particles also diminish over their lifetime by manipulating the density channel. Just pick this that we already used as the multiplier. Oh, I made a mistake once again. I forgot to add 1. Alright, perfect. Okay, now it's time for our second and last Magmaflow. I'm choosing by the material index and I'm checking if it is a particle with the material index channel value of 1. And if this is the case, the already existing emission channel from our first Magmaflow will remain our emission channel, same as with the density channel right here. But if not, then we will do a couple of changes. But I'm lazy, I'm going to copy all our operators of this Magmaflow, go in here. But of course I will change some values from specific operators. Okay, delete this. I want to get higher values of the velocity magnitude, so I'm going to divide it by 1.5. To the power of 2 is still correct, but I will add a value of 3. But the h should diminish a little bit faster, so it gets divided by 10. But I'm going to let more particles be flickering ones. So I'm turning down the maximum of our uniform random to 100, same as with the modulo. But the brightness will be very high, so the final scale or final multiplier of our gradient ramp will be 5 instead of 0.4. And then we have it. Also the density this time will be multiplied by a value of 20 and put in here. Okay, let's take a look. Yeah, that's pretty cool. We can see the splines a little bit better, but there's one last thing to change. And this would be the color ramp. This here is already correct, but we don't want to go so much into red. Violet will be perfect for us. Okay, that's cool for our first gradient here. But for the second Magmaflow, I would like another one. Press Shift, drag the gradient ramp aside. Repeat that 2 times. Put it in here. and here, and now I'm going to change both. So with the first value, it would be a little bit more azure, or however you call it in English. And the other color of the first gradient will be more blue and more dark. Oh, that's okay. And in our second gradient, we will also change the colors. Here a little bit more into violet. But again, more into the bluish and not so bright again. Okay, that's perfect. And last but not least, not linear, but box. Okay. Drag a wire and place it in the sample slots. So we have access to it in our second Magmaflow. Yeah, we will replace our gradient ramp with this instance, of course. Okay, now it's time to go right into our camera. Take one look again. Cool. So now it's time for setting up the loop. How do we do that? First of all, I'm going to rename it. I'm simply calling it PRT001. Going back out of the camera. Then I'm going to copy it 3 times. The fourth one will be called PRT000 for the chronological order. Because now I'm going to set up the loop, and I'm going to do this by letting this loop be existent when the rendering starts, and this can simply be done with a frame offset of 450. Then PRT001, nothing changes in here. And here, this is the PRT loader which starts at frame 450. So we will make a frame offset of -450. And then our last PRT loader is going to be played when the first PRT loader is finished with playing at frame 900. So this will have a frame offset of -900. So PRT loader 003 shows us from frame 900 the first 450 frames, which will be continued by PRT loader 000 at the beginning of our animation. So both have to show us partition number 3, same as here. Yeah, and the other ones will show us partition number 1, which is already here, and partition number 2. Okay, there it is. Disable this, because we will see the whole range of their partition from 0 to 900, and here from 450 to 1350, which will be the end of our animation or our rendering. So I'm going to change the end time of our time configuration. So now there's only one thing left. This PRT loader must be at 50, while our original PRT loader is at 000 position. The next will be, maybe you can imagine it, at -50. And this will be at -100. So our camera, which will be at the beginning at 375, will show the exact same loaded frame, not from PRT loader 000, but from PRT loader 003, which is exactly 150 meters away. So our camera should be also 150 meters away. So it's very simple to make the keyframe. Finished. The light itself has a very big hotspot and a follow field, because all particles shall be enlightened from the same angle and they all will have the same amount of light. So as long as they are in the hotspot region, everything is cool. Here, take a look at this. Last frame, first frame. Yeah, it's all safe. Last but not least, for rendering, of course we will render it with depth of field. So take the Krakatoa camera modifier and put in this that I already tested, which looks pretty cool. And sure, I will render with motion blur enabled. Jittered motion blur, adaptive motion blur, of course, with passes between 1 and 12. Depth of field, sure, with a quality of 1 or higher if you want to, but this could also increase your render time. And because frame number 1350 is the exact same frame as frame 0, you should end 1 frame earlier with the rendering. I hope you don't forget to change to your camera, enable all the PRT loaders, of course, and most important, thank you so much for 1000 subscribers. That's so cool and I'm so thankful for that. I really appreciate. And I hope you enjoyed, and I hope it wasn't too complicated, but I hope you could learn something. And send me your feedback, tell me your questions, or tell me your ideas if you wish another tutorial on something else, maybe from my projects, I don't know. And of course, feel free to use my free VJ loop. It's my Christmas gift to you, and I wish you all a happy new year in 2021. Bye bye.